Hello and welcome back. We're going to continue our discussion with what a line integral is. We're not going to go into a very rigorous proof of it, but more of an intuitive one. Just to give you an idea of what a line integral does for us and how we can find it. If you're looking for a more rigorous one, there are plenty of videos out there on YouTube. It is a little bit more lengthy and very difficult, so it's a little bit above our pay grade right now. Simply, the idea of what a line integral is imagine we have a path right here, and we project it to the xy plane. We would get something similar looking like this. And you can imagine like a sheet or a wall here, and we want to find the area of that wall. So that's what a line integral does. It gives us the area between the xy plane and the path. And that's what we're going to be looking for today. So let's talk about how we do this. Just like in BC last year, or Calculus 1 or 2, we're going to draw a rectangle. We're going to pick two of these points and we're going to draw a rectangle. Now about this rectangle, I know some information. One, I know its height is a function xy, is f of xy. I also know this base right here, which we're going to talk about. This base is our problem. When we go to what we did in Calc 1, if we were to draw our rectangle, of course, our height is f of x. Our base just deals with the change in x, hence area, height times base, whatever. And that's the area of our rectangle. The problem is, when we get to more than one dimension, or two dimensions, like a three-dimension like what we have here, our base isn't so simply in terms of x and y. Our base is in terms of both x and y. There's a change in x and there's a change in y. And it's more difficult to deal with in terms of x and y. So this is why we're going to work with parametrics. So for the base, we're going to use parametrics. Now, this base is also on this projection. I know that I can find the equation of this projection, and this little piece right here is an arc length. So the base is an arc length, which we use, which we call S. And to find the arc length, it's a lot easier in parametrics than it is in any other form. So that's the reason why we really want to use parametrics. So let's talk about the area of a rectangle. We know from Algebra 1 that the area of a rectangle is the base times the height. Well, if I were to write this now, my area here would be the base, which would be my arc length, times the height, which is f of xy. Right there. So another way I could write this, I'm going to switch this around, you'll see why in a second, f of xy times s. That's my arc length. Right here. Now, so that's my area. Now, what we're going to do, just like in everything calculus, if I want to get more accurate, I let this arc length get really, really small, so it becomes ds. So we would get f of xy ds, a very tiny little sliver of that arc length. And we would integrate that from over our curve, where C is the curve. It's the domain of our curve right there. Now, this right here is the equation of a line integral, f of x ds. But the problem is, ds right now is in terms of x and y. And what would we just say? That is not very friendly to do. ds is, oops, sorry about that. ds is not easy. So we are going to convert to parametric. Now, we did this in another video. But simply put, the function is easy to convert. That's just going to be f of x of t, y of t. But the ds part is my arc length. So ds from earlier this year we said was the integral of x prime of t dt squared plus y prime of t squared dt. And check out my earlier videos. We kind of talked about this. We used the Pythagorean theorem. We can be able to prove all this. So this is going to be multiplied by all of that. X prime of t squared plus y prime of t squared dt, and from A to B, where A and B are in terms of t. This is going to be our formula to get the area of this wall right here. Now, simply put, a line integral is the evaluation of an integral over a smooth curve with a density equation incorporated in it. So really, if we think of f as my density equation, this, remember, this is the length times width. That's like this little tiny little area of our arc times density gives us mass. So these are little formulas in 2 dimensions and in 3 dimensions or more, where C, remember, C is the curve. It's the domain on our curve that we're looking at. So let's look at an example right here. You can look, let's look at an example. From example 1, evaluate the line integral over the interval 0 to 1 given our density function is x plus y plus z. Well, from example number 1, we said x was equal to 1 or t plus 1. We saw that up here. Example number 1, 1 plus t. Y was negative 5t plus 2, and z was t minus 1. The first thing we're going to have to do is convert. So we're going to convert. We have to convert rho to parametric. So to convert rho to parametric, let me just rewrite that. There we go. To convert rho to parametric, we would get x, which we know is t plus 1, plus y, which is this negative 5t plus 2, plus z, which is this t minus 1. And that's going to give us, what's that, negative 3t plus 2. So now I can go ahead and set up my equation. To solve my integral, and this is going to give me my mass in this case, we'll talk about that in a second, from 0 to 1, we're in terms of t. Everything has to be in terms of t. My function, which is this negative 3t plus 2 times ds. Remember, this little piece right here is ds. So what does ds need? Remember, we need all the derivatives. So I know x prime is 1, y prime is negative 5, z prime is 1. And if I plug those in, 1 squared plus negative 5 squared plus 1 squared. And I can evaluate this. It's not that hard. This is just the square root of 27. It's a constant, so it just goes on the outside. And I don't even need to do this. I can integrate this right away. We get negative 3t squared over 2 plus 2t, and we evaluate that from 0 to 1. And let's see what we get. The square root of 27. I don't have to worry about the 0, so we just get negative 3 halves plus 2, whatever that is. And remember, this is going to be a mass. If this is the area of my base, that's the area of my base, and this is my density function right here. Density times area gives me the mass of that sheet, or that wall right there. Very skinny wall, though. I hope you enjoyed the video. Go to video number 3 and we'll take a look at a couple more examples.